Section 8, the relationship between Ka and Kb. So we know that there's going to be a relationship between Ka and Kb because we know that Ka is related to pH. We know that Kb is related to POH, and we know that pH and POH are related through the equation pH plus POH equals 14. So moving on, we know that Ka is for an acid equals the concentration of the products over the concentrations of the reactants. Same thing for Kb. These are just some examples. This is the most important thing to know. Ka times Kb equals the concentration of H plus times the concentration of OH, which of course equals Kw, which in turn makes Ka times Kb equal Kw. We already know what Kw is. We know that Kw equals 1 times 10 to the negative 14, and that's on the reference table, and so is this equation. So whenever you need to plug into this equation, and you'll be given something like Ka or Kb, or even you'll find it, all you have to do is plug into the equation. You already know Kw, so then you just use algebra to solve for it. So you subtract it from one side, or you divide it by 1 from one side, and that's that. Here it's saying again, Ka times Kb remains that at 25. 25 is just the temperature that most reactions are done for acids and bases for our purposes. Okay, so here's some of the examples of acids and bases. Moving on. pH equals the negative log of that. How many times have we seen that now? You should know now that P equals negative log. Okay, so pKa or pKb. So what does the P stand for? Negative log. So what is pKa? It's the negative log of Ka. What is pKb? Negative log of Kb. It says it again down here. pKa equals negative log of Ka. pKb equals negative log of Kb. So again, we know that pKa plus pKb equals pKw, and that equals 14. And this can be derived from the equation from Ka plus Kb equals Kw. We know that pKw equals 14 because we looked at that earlier when we were looking at pH and POH. A lot of this is very confusing to derive. You're not going to need to worry about that. Just know the formulas. Most of them are on your reference table. Not sure if this one is, but I know the other ones are. So just plug into those equations. Besides that, you're not really going to use them for much else. Even before this chapter. Okay, section 7, acid-base properties of salt solutions. So this is just a culmination of all the knowledge from the previous sections. Type of reaction is called hydrolysis. Hydrolysis is ions reacting with water to generate H plus and OH minus. pH of an aqueous salt solution. Okay, so in this section, we're basically going to go through the steps of determining if a aqueous salt, so a salt that's in water, is going to make the solution more acidic, more basic, or if it's not going to change it at all. And anion's ability to react with water. So talking about anion, remember, if you were to draw, or if you were to write out the thing for a salt, you're going to have A being your cation and B being your anion. So I'm just going to write cation, anion. Remember, cations are positive, anions are negative. If you forget that, just think of any substance. So HCl, the H is positive, Cl is negative, Cl is the anion. HA is, sorry, let me erase this. HA is not one of the 7 strong bases or strong acids, it's a base. Okay. So this is just talking about how strong the conjugate base is. So if Cl in HCl is the anion, then A in HA is the anion as well. If HA is a strong acid, then A is a very, very, very weak base. Remember, strong acid, weak base, strong base, weak acid, strong base. It's opposites. Just basically knowing the rules about the conjugates is all you need to know for this. So if it's a strong acid, it's going to have a weak anion. If it's a weak acid, it's going to have a stronger anion, stronger conjugate base anion. So just follow along with those rules to determine how strong the anion is. And then determining cations. Cations are formed from the bases. It's the same thing for anions here, is that if it's a weak base and a strong, it's a weak base, it's going to have a strong conjugate acid. I don't know why I can't speak today. If it's a strong base, it's a weak conjugate acid. It's all they make this a lot more complicated than it has to be using Kas and Kbs. You just got to know your conjugate base and acid rules. So now when we combine them, you can remember which of them was strong and which of them was weak. So if you there's 4 rules for determining how a salt affects something. You're going to look at the salt. Here's how you're going to figure it out. You're going to look at the salt and you're going to figure out what was the acid and what was the base that were used to neutralize. Remember, when an acid and base are neutralized, they create water and a salt. What were the acid and the base used in the neutralization reaction to form that salt? So we'll look at NaCl. So we have NaCl. What formed that? It was NaOH and HCl. Both of these are equally strong. NaOH is a strong base. HCl is a strong acid. So since NaOH is a strong base, what kind of conjugate is it going to have? It's going to have a very, very weak conjugate acid. And since HCl is a very strong acid, what kind of conjugate base is it going to have? It's going to be very, very weak. So a weak conjugate acid and a weak conjugate base are going to neutralize each other out. I'm going to change that word. Not neutralize. They're going to cancel each other out, making the salt neutral. So NaCl, any of these that come from 2 strong acids are not going to affect the pH. If you're looking at salts that, such a case would be Ni as conjugate base of a weak acid. Okay, so if the conjugate base is of a weak acid, so that means it's going to be a stronger conjugate base. The cation, okay. So part 2 is talking about a stronger conjugate base and a still weak conjugate acid. So you're going to have NaOH, which is a strong base, so it's going to form a weak conjugate acid, and ClO, which comes from HClO, which is a weak acid. So you've got a weak acid, strong base. Strong base is going to form a very, you know what, let me draw this out just so you can follow along. You got NaOH, HClO. Those are your 2 originals. How do I figure that out? You just got to look. This is your anion. This is your cation. Cations are formed from bases. Anions are formed from acids. So this is a strong base, so it's going to have a very weak conjugate acid. This is a weak acid, so it's going to have a relatively stronger conjugate base. So a relatively stronger conjugate base with a very weak conjugate acid means that it's going to be basic. So these salts that are formed like this are going to affect the pH, bring it up, and the same effect that a basic substance would have on it. So this is the vice versa, is if you have a weak conjugate acid, a strong conjugate acid and a very weak conjugate base. The weak conjugate base comes from a strong acid, so HCl will have a very weak conjugate base. The relatively strong conjugate acid will come from a well, I shouldn't say relatively strong. It's stronger than the other acids that a strong base would form, but it's still considered a weak acid. The weak acid comes from a weak base. So when you mix a weak base and a strong acid, you're going to have a acidic salt substance, which is obviously going to make the solution more acidic. So then our last type is if you have a weak acid and a weak base. So a weak acid is going to form a weak conjugate base. A weak base is going to form a weak conjugate acid. And you can tell right from that whether the solution is going to be an acid or a base. So you have to look at the Kas, and whichever conjugate acid or base is stronger, the salt will have the properties of that. So if it has a stronger conjugate acid, then a stronger conjugate, then if it has a stronger conjugate acid, then a conjugate base, then it's going to be acidic. If it has a stronger conjugate base than a conjugate acid, then it's going to be basic. If that's too hard to follow, I'm going to give you some simple rules. A strong acid and a strong base form a neutral salt. A strong base and a strong base and a weak acid forms a basic salt. A strong acid and a weak base forms a acidic salt. And a weak acid and a weak base, you have to look at the relative strengths of the conjugates. So moving on to section 10. Acid and base behavior and chemical structure. When a substance is dissolved in water, okay. This is just talking about the structures. So let's get into the section. We'll discuss them a little bit. Factors that affect acid strength, bond polarity. Bond polarity is the difference between the electronegativity of two elements. So you'll have H and A. A is not actually an element. A can be fluorine, chlorine, anything like that. A is going to be more electronegative, so the electrons are going to shift towards the A. And that's what creates the polar bond. Remember that back from when we were talking about 3D structures. Bond strength. Bond strength also helps determine very strong. Okay, so the general rule is that bond strength also affects the strength of an acid. The stronger that a bond is, the harder that it's going to be for something to dissociate. The weaker the polarity, also the less chance that it's going to dissociate. So that is important to know because it explains why something like HF is not a strong acid. Because even though HF is more of a polar bond than something like HCl, it's such a strong bond strength that it's not going to dissociate. Remember that in order for it to dissociate, you got to have the two ions separate from the original substance. So if you have HF, it wants to break down into H and F, but since the HF bonds are just so strong, there's a lot of them that can't break it apart into those two. So that explains why HF is a weak acid. Here is it saying, in general, as the HA bond strength decreases, stronger the acid. So the weaker that bond becomes, the stronger that the acid is, because it's more easily able to break into its different ions. Conjugate base stability, in general, the greater stability of the conjugate base. This is just something you should memorize. The greater the stability of the conjugate base, the greater the stronger the acid. Stronger acids, more stable conjugate bases. Okay, binary acids. For a series of binary acids, blah, blah, blah. Binary acids are hydrogen and one other substance. So HCl, HF, HI, HBr, all binary acids. So H and something else. Binary, they can be represented by HA. Bond polarity is a major factor determining acidity. Although NH is a polar, the non-bonding okay. If you get anything out of this, just know this table. As you go down, it becomes a stronger acid, and as you go to the right on the periodic table, it becomes a stronger base. So HF is a weak acid. Going down, HCl is a stronger acid. And then by this trend, HBr would be a even stronger acid than HCl. Same thing here. H2O, generally neutral. Going down, H2S, remember it goes oxygen then sulfur, is going to be stronger. And then Se is going to be stronger than S. And then going to the left, ammonia is going to be a weaker base, is going to be a stronger base than pH3, because remember, it's getting more acidic as we go down. And then these are just neither acidic or basic. So as you go to the right, it becomes more acidic. As you go down, it becomes more acidic. Okay, oxyacids. Uncommon acids, such as sulfuric acid, contains multiple OH bonds. Remember, for oxyacid, the general rule is that if there's 2 more oxygens than hydrogen, it's a strong acid. The only exception to that would be HClO4. Anything more can be, as long as it doesn't have a carbon. If there's a carbon, you can throw that rule out the window, because that can all change. When Y is a nonmetal, generally as the electronegativity of Y, so this is the acidity of the substance. Okay, so this is just talking about the structure of oxyacids. This happens for 2 reasons. First, the electron density is drawn. Yeah, so this is just talking about the structure. So we'll look at something like HSO4, which is sulfuric acid, which is strong. H2SO4, sorry, sulfuric acid, which is a very strong acid. You'll see you'll have the hydrogens bonded to the oxygen here. You'll have the OH bond. And the only reason that acidity changes is because polarity changes. So you got SO4, which is the strongest acid, or H2SO4, sorry. And then H2SO3 will be a weaker acid, because the less oxygens, this is a general rule, the less oxygens the substance has, the weaker an acid that it becomes. Carboxyl acids. Carboxyl acids are another name for organic acids, and it's an acid that has a carbon element in it. So we'll have something like formic acid. So you see, you got the carbon bonds here, benzoic acid, carbon bonds. All you should know is that carboxyl acids generally behave like weak acids, weak organic acids. So then just like that, they'll have stronger conjugate bases, and they'll act just like all the other weak conjugate or weak acids that we talked about. So our last type, or our last section, is Lewis acids and bases. This is the last type of naming, and this accounts for the different types of acids and bases that don't follow the Bronsted-Lowry and the Arrhenius definitions. And what Lewis says is that a acid is a electron pair acceptor, and a base is an electron pair donor. That's the opposite of what the Bronsted-Lowry theory said, because the Bronsted-Lowry theory said that an acid was a proton donor. So an acid is a proton donor, but an electron acceptor. A base is a proton acceptor, but an electron pair donor. So again, the whole theme of this chapter is opposites, talking about conjugates, talking about these definitions here. Just know that they're opposites, but they can be used to classify things the same. So if something's in a Lewis acid, it's not going to be a Bronsted-Lowry base. It's still going to be a Bronsted-Lowry acid. It's just they have different ways of defining them and determining them. So here's just a good example. So you have the hydrogen and then the NH3. Remember, NH3 is ammonia, and ammonia has this extra pair of electrons here. So these electrons are going to be donated to the H plus to form this HN bond. So the H is going to accept the electron pair, making it the acid. And then, you know what? We'll leave it like this. The H is going to accept the electron pair, making it the acid, and then the NH3 is giving away the electron pair. So it becomes the base, the Lewis base. Easiest thing to do is just to memorize these definitions, and then you can apply them again here, the electrons are being donated from the N to the B. So this would be a Lewis base because it's donating the electrons, and then this would be a Lewis acid because it's accepting the electrons. And the only reason that this theory is in place is to help explain for things that don't purely fit the definitions of the Bronsted-Lowry and the Arrhenius theories.